We've talked about how internal energy or heat or thermal energy, all pretty much three terms for the same thing, is the kinetic energy of the atoms and molecules inside a substance. So that's the energy that's stored in the material of something due to the vibrational little kinetic energy of the atomic parts of that material. And the quantity that we use to characterize or one quantity we use to characterize how much energy is in there is the temperature. So the temperature is a measure of the kinetic energy of those pieces. However, it depends what that stuff is made of because different atoms and molecules have different masses and they have different abilities to vibrate depending on the structure of the material. And so in this part of the module, we're going to be talking about a material property called the heat capacity. And the heat capacity is something you look up, you don't need to memorize it, and it describes how much energy results in a change of 1 Kelvin temperature of a kilogram of material. You'll see heat capacity or specific heat capacity listed. Specific in this context doesn't mean you're being very precise. Specific is a term in this context that is used to mean per unit mass. So that's just some physics jargon. So the specific heat of aluminum, as shown in this table here, is 900 joules per kilogram per Kelvin. And what that means is it takes 900 joules of energy to increase the temperature of 1 kilogram of aluminum by 1 Kelvin. On the other hand, it takes only 502 joules of energy to increase the temperature of 1 kilogram of steel by 1 Kelvin, according to the information in the table. And on the other end of the spectrum, it takes over 4,000 joules of energy to increase the temperature of 1 kilogram of liquid water by 1 Kelvin. So that means if I take, say, for example, 4,000 joules of energy, I put it into a kilogram of water, a kilogram of aluminum, and a kilogram of steel, I'm going to get different temperature changes for those different things. The water is only going to go up by 1 Kelvin. The aluminum is going to be more than 4 Kelvins hotter, and the steel is going to be about 8 Kelvins hotter. So you see different temperature changes because the same amount of energy results in a different degree of motion of those materials, of those atoms and molecules in the material, and the demonstration in this module illustrates that as well. So that specific heat we designate by the small letter C. That's a material property, that's a constant. This equation is an equation you'll be using in the homework, relates the amount of energy that results in a given temperature change to the amount of material and the kind of material. So previously, when we just sort of generically defined thermal energy and said temperature measures the thermal energy, you might have thought, well, energy equals temperature change. But it depends on how much material there is, of course. So it takes twice as much energy to increase the temperature of 2 kilograms of material by 1 Kelvin as it does to increase the temperature of 1 kilogram of material by 1 Kelvin. So then we see that the energy equals the mass times the temperature change. And then we have this new constant, the specific heat capacity, the specific heat of the material in there, this little c, which is something you look up, and that relates the temperature change delta T, which has to be in kelvins, to the amount of energy that is put into an object. So, and equivalently, you could use this to say if an object loses or gains a certain amount of energy, how much will its temperature change by? So the equation here is pretty straightforward. If I want to change the temperature of something by, say, 6 Kelvin, I put delta T equals 6. I would look up what the specific heat of that material is. I would say how much of that material do I have to heat up by that much, and then I would multiply those three things together, and that would tell me how many joules of energy do I need to put into it to get that temperature change? On the other hand, if you said that something gained, if I put a heater on something or a power source into something and I'm putting in 1,000 joules of energy, what's the temperature change? I would just rearrange this equation to say delta T equals Q divided by MC. So the example on this slide works through that, where the question says that there is a hot water heater that holds 40 gallons of water, and it is heated at a rate of 5 kilowatts. Remember, that's a measure of power or energy per unit time. So that says we're putting 5,000 joules in per second into the water, and after your sister has taken a shower, the water temperature is 90 degrees Fahrenheit. You want to heat the water back up to 120 degrees Fahrenheit before you take your shower. How long will it take? So that's the description of the situation. We know we have 40 gallons of water. I have to convert that to kilograms. So I look up and I find that there's 3.79 kilograms is the mass in a gallon of water. So I can convert my 40 gallons to kilograms, and I get 151.6 kilograms. My temperature change that I want is 30 degrees Fahrenheit, but my specific heat is in joules per kilogram per Kelvin. So I have to convert that 30 degrees Fahrenheit temperature change into a number of kelvins, and that conversion factor is 5 divided by 9. So a Kelvin is larger than a degree Fahrenheit, almost twice as large. So there are 5/9 of a Kelvin in 1 degree Fahrenheit in terms of a temperature change. So that 30 degree Fahrenheit temperature difference becomes a 16.7 Kelvin difference. And the specific heat for water is 4,184 joules per kilogram per Kelvin. We multiply all that together and we get 10 to the 7 joules of energy. So how long does it take? Well, I'm putting energy in at the rate of 5,000 joules per second. So I take the amount of joules that I need, 10 to the 7, divided by 5,000 joules per second. It gives me 2,000 seconds, or about a little over a half an hour. The other aspect of internal energy that we need to be aware of is the energy required to change the phase of matter. And by phase, I mean solid, liquid, gas. So if we stick with water, water can exist in a solid, we call ice, liquid, water, or steam. And it takes energy to convert solid water to liquid water, even without changing the temperature of it at all. And that's called the heat of fusion. That's the energy involved in the transformation from solid to liquid or vice versa. And there's the heat of vaporization, which is the energy involved in transformation from liquid to steam or vice versa. Those two amounts of energy are called latent heat of transformation. And they are numbers that you look up. And so the figure in the upper right here shows the latent heat of transformation for water ice is 0.334 megajoules per kilogram. That means it takes 334,000 joules to melt a kilogram of ice. And when you do that melting, the water will still be at 0 Kelvin. There's no temperature change during that phase change. The latent heat of vaporization of water is bigger. It's over 2 million joules per kilogram. And that means if I want to evaporate a kilogram of water, it will take 2.257 megajoules of energy. And when I put that amount of energy into the water, I will, into that liquid water, if it's already at the boiling temperature, 212 degrees Fahrenheit or 100 degrees Celsius, it will not get any warmer. And that's what this plot on the lower right is showing, that as I put energy into a substance, the temperature increases. That's what is explained in this equation here. Put energy in Q, I get a delta T out. That's as long as there's no phase change. But if I reach the melting point or the evaporation point, those temperatures, then you'll notice that this line for temperature becomes horizontal. And the entire time I'm putting more and more energy into that solid after it has reached its melting point, that energy is only going into converting the solid to a liquid and not changing the temperature of it at all. And similarly, once I put energy into water that's at the boiling temperature, the water will not get any hotter until all of it is converted to gas.